Okay, continuing on, we were on number 11, so we've still got a kid on a merry-go-round. Now we want to find out the centripetal acceleration. Remember, if you're moving in a circular motion, you're always going to have this centripetal acceleration as well that's pointing towards the center of the circle, okay? And we have an equation we already know for this, which is v squared over r. We can also express that in terms of angular velocity. If we use the bridge equation for this, we've got r omega squared divided by r. We end up with r omega squared. And so in the case of this question, we're given this angular velocity and a radius of the merry-go-round, and so we can use that to get our centripetal acceleration. Because we don't easily have linear acceleration here, or linear quantities here to use this version of the equation, but we're given these items without having to do anything else. Number 12, this is another one we have not gotten to, and we will look at after the break, but this is where we combine translational and centripetal acceleration into a combined linear acceleration, and that's going to involve the Pythagorean theorem. I'm not going to go too much into this one because this isn't going to be covered in this week's test, and we need to look at it when we come back, so we'll hold on that one for now. Let's see. Okay, we got an astronaut and a centrifuge, so they're being spun. And we want another angular velocity at 12 seconds. We're given a radius. We're given, starting from rest, we're given an acceleration. So we want like a final velocity here. And based on all our givens, we could use this equation. This is the first of our motion equations. So we put in our initial velocity at rest, acceleration time. We get this value for the angular acceleration. Then same astronaut, we want to know what's his centripetal acceleration. So we're going to use the same equation I just talked about. This is our centripetal acceleration in angular form. And so we put the numbers in, get this. What's his linear or tangential velocity now that we've got his final angular velocity up here. So we're going to put that in down here in this question and use the radius of his centrifuge to get a linear velocity. So that's using the bridge equation again. Bridge equations are really handy with angular to linear motion or vice versa. Tangential or translational acceleration of the astronauts. So same bridge equation again. This is the acceleration one that we haven't looked at as much. And we had this acceleration from the previous page. That was already a given, as well as the radius. So we're just putting those numbers in here. And note, this gives us a linear quantity, like linear units, meters per second per second. Okay. A flywheel has a constant angular acceleration of 7.8 radians per second. The tangential acceleration of a point on its rim is, so this is another bridge equation, but we have to do one quick thing, which is convert diameter to radius. Remember, diameter is, radius is half of diameter. Okay, diameter is like the full segment that bisects the circle, and then radius is half of that, so I get half of 1.1, and then I use that in the bridge equation. And then finally, this is actually one that I had in the stations for the velocity, the bridge equation stations that we did last week. We have the roulette wheel, the ball's rolling around the inside. We've got revolutions per time for the ball, and we want to know where it's going to be at 2 seconds, so we can figure out its angular velocity. This is a constant velocity question. So we're given 2 revolutions, which is 4 pi, per 1.2 seconds. Gives us an angular velocity of 10.5 radians per second. And then we can put that in to this equation. This is our constant velocity equation, just solved for displacement, because that's what we want. Angular velocity times time, so it will be at a 21 radians, or it will have gone about 3.3 revolutions at 2 seconds, based on this given in terms of how we get its angular velocity. So, okay, that's all the problems.